Welcome to the Advanced JVM Tuning Talk. My name is David Keenan. I am the Java Platform Performance Architect at Oracle. I'm here with Monica Beckwith, who is our lead performance engineer on garbage collection. And we're going to go through advanced tuning. Now, we have a lot of content. There's a good chance that we're not going to get through it. We try to make these slides as understandable and standalone as possible. So bear with us as we try to go through this quickly. Okay, you've all seen this before. All right, first is an overview. All right, so basically, what are we going to talk about? We're going to talk about advanced tuning strategies. These are ideas that we have as far as new ideas for JVM tuning, new ideas for configuration tuning of the JRE, things you should look at as far as operating system tuning is concerned, and quite a bit on garbage collection and methodologies as far as tuning for both throughput, low latency, and footprint. Big message with tuning: your mileage is going to vary. Not every tuning parameter is going to help you. And sometimes bad tuning can hurt you significantly with performance. So one thing at a time, one flag at a time, if possible. Actually, not if possible, one flag at a time. Make sure you understand what you're measuring as you go through a tuning process. Lastly, as far as our slides are, as far as our tuning parameters are concerned, hey, you can go Google hotspot tuning parameters, and there's got to be close to 500 of them. Well, we should have been more careful, to be very frank. But there are a smaller set of flags that we highlight and we talk about on a regular fashion than we have on our VM options page. Try to stick to those. If they're not on our standard pages, not only may they not impact performance at all, but also they may change. So our development methodology has always been, hey, let's try something new. Let's have a flag around it, because that allows us to turn it on for development testing, turn it on for performance testing, and all those flags are now public. So just keep that in mind. We have a project for JDK 8 to clean up our flags, and we understand it's confusing, and we are certainly trying to fix that. So let's go right into tuning approach. There are two general methodologies. Of course, there's more, but there's two general methodologies that we employ for going after performance tuning and analysis. The first of which is a top-down analysis approach. This is the most common approach for software performance tuning, mainly because you're looking at your software application top-down. Right, so your application's largest contributors to performance problems, your bottlenecks, your algorithms that could be optimized, is really what you're going after. You use this type of methodology when you can change the code at the highest level of the stack, your code. All right, so you're basically going to start off monitoring your application under load. This is both OS performance monitoring and JVM performance monitoring. This will give you an idea of where your potential problems lie. Is it paging in the operating system? Am I spinning on a lock? Is it garbage collection that my problem is? Once you get down the path, get past what you can monitor within the JVM and the operating system, you're then looking at what's going on at the application level and the kernel. Right? It's not just your application per se; it's also the other software running on the system, the operating system. And that kind of gives us an idea of what we can do as far as OS and JVM tuning, both at a tuning parameter level, but also at changing your code. Now, I speak specifically about OS and JVM. I'm speaking how our approach here. And you can apply these approaches to your own application spaces, but when we look at software per se, it's software above the hardware, operating system, JVM, Java runtime, virtualized environment, and so forth. Here's our nice diagram showing this. Notice on the left, your application is under load during you do that while you're testing. It should be what you're anticipating and what your test environment, a reasonable, realistic load. Start at the top at the OS. The OS will give you an idea of, that's your first space to look. You're going to look at the CPU's information that you get from the operating system through MPStat, VMstat. There's a slew of tools to give you that information. Also the I/O operating system, I/O subsystem, network, and so forth. Next is the JVM after that. once you get to pass your JVM as far as taking a look at the information that's available to you, is you move to profiling your application, tuning, and then code modification. And then it starts all over again. Second approach is a bottom-up analysis. Bottom-up analysis is very powerful when you're trying to optimize for a specific hardware platform. And it's used when you're not, and also you use it when you're not able to change the code at the application level. Product deployments that are already deployed, competitive benchmarks where you're not able to change the benchmarks, is where we find ourselves using a bottom-up only approach. You're gathering statistics at the lowest level of the stack, both CPU statistics, cache misses, network statistics, I/O as well, and you're able to modify the lowest levels of the code to impact CPU efficiency. So that's the JVM, and you can't level. You're not able to modify the highest levels of the stack. You're stuck modifying the lowest levels of the stack. And here's a nice graphic showing us that approach. Start with monitoring the CPU, profiling your application with hardware counters, identify your problematic instruction sequences, tune, modify OS, JVM, code generation, data libraries, basically everything under your application. Now, it's not one of these approaches or the other. I would highly suggest starting with a top-down approach. A top-down approach will yield the largest performance improvement initially. Your largest performance improvements are going to come from algorithmic changes in your code. Simple as that. The JVM and the operating system we do the best we can with the code that's handed to us. So you have the most power as influencing your performance. However, once you've exhausted what you can do in a top-down analysis, eventually you're going to be pointed to a method where you're like, wow, I don't no idea how I could improve performance in this method. And that's where the bottom-up approach comes into play. And the joining of those two methods tells you, hey, that method that I have no idea how to improve the performance, actually it's a cache miss. And it's a cache miss because I'm accessing this data structure. And that's the type of information you get from the bottom-up approach. With that information, you can make your code changes. Or at least try. It's not always that simple. So again, it starts over again. Once you make your modifications, you've got to start monitoring all over again to make sure it actually influenced what you expected it to. Okay, so that's our general overview of approach. Now we're going to go into general advanced tuning. So this is chasing the last 5% of performance optimization. The areas that I'd like to cover are JVM tuning. And these are little bits that you should be aware of. I'm not going to go down the methodology as far as going through advanced tuning methodologies. It's not. This is how you these are the tips of getting that last 5% for you. So JR runtime configuration, OS tuning, and deployment considerations as well. So starting off with JVM tuning. The first thing to consider is dynamic compilation and some new features we have in tiered compilation. I mentioned this briefly in a talk yesterday. Tiered compilation is our new merger of the traditional client compiler, which we call C1, and the server compiler, which we call C2, and the interpreter. We always interpreted first. We would use instrumented code in the interpreter to make decisions on what to compile in C1 and C2. And in this situation with tiered compilation, we interpret. We are gathering information in the interpreter to determine what we're going to compile in the client compiler at C1. C1 will generate instrumented code for us to make decisions on what to compile in C2. So we're getting a much better information as far as where our true hotspots are, because we are instrumenting and compiled code, and we're making our decisions in C2 based on instrumented C1 code. Compared in the past, we would make our decisions based on instrumented interpreted code. This is not on by default, and the main reason it's not on by default is that the current heuristics that we have surrounding the code cache are insufficient. The code cache is where all our compiled code goes. We knew that we needed more space. With tiered compilation, the problem is that it was much more space than we anticipated. We increased the size of the code cache to 96 megabytes from 64 with tiered compilation, and it simply isn't enough for very large applications. So we saw situations where we were putting a lot of pressure on the reserved code cache, and if you were out of code cache, you stop compiling. We do have ways of cleaning out the code cache, kicking out code that is that's old, that doesn't need to be reserved. But you can imagine a situation where we're putting a lot of pressure on the code cache, and we've got this new code that will clean out the code cache, and we're basically kicking out code all the time. So we have to tighten that up. So that's not on by default at this point. But I do highly suggest you take a look at it, because for a large majority of applications, actually most applications, you're going to see a performance benefit. It's those corner cases that we're concerned about, where in those very, very large applications, I'm talking hundreds of thousands of classes.
Is this in JDK 7 or is it available in the previous version?
It is. Its use is supported in JDK 7. Yes, 7 update 4.
Code cache on a heap or permgen? Where is it stored?
It is a native space. It's not in the heap, and that will continue to be the case.
Is it update 4?
Update 4, yes. Update 4 was a very large performance change for us for 7. We see most of and most of the workloads. Actually, all of the workloads in which we use tier compilation with a appropriately tuned reserved code cache, we see performance benefit. It's just that we don't have the heuristics in order to do that automatically yet. We will. Okay. Another thing to be aware of is I'm sorry. I'm using a view for my display here that's a little different. So I apologize. Runtime tuning parameters. Always pre-touch. We allocate the heap up front as you start the JVM. We allocate the heap. But we don't touch those pages until you actually need them. So it's reserved up front, and then we'll actually fetch them from the operating system and request them from the operating system as you need those pages. With very, very large heaps, and when you're rather performance sensitive, especially at the beginning of the launching of your application, you don't want to take that hit of faulting in those pages. So we have a flag to pre-touch them up front. So all of them be, you'll have access to them. You won't take that hit from faulting the pages in. I'm sorry, the question was? No, I'll cover that. I mentioned that twice here. Unfortunately, I make sure that I have that. Yeah, we'll go again. No, so just to finish the comment on always pre-touch, it is worthwhile if you're seeing a performance hit and you're using a very large heap, it's a worthwhile flag to test, because touching the pages up front will avoid that overhead. Huge pages or large pages is also something you want to consider. On Linux, here's the 2 flags that you want to turn on. I have another slide that further on that has a bit more detail. Okay, system dictionary. The system dictionary is a data structure in the heap that stores unique loaded classes. And it's a hash table. It's a locked hash table. And its default size is 1009. So you imagine if you have more than 1009 distinct classes loaded, you start to have a performance impact from the system dictionary. A large majority of applications aren't running into this problem. However, if you're doing profiles and you see something related to the system dictionary, increasing the size is something that will be helpful to you. And I have a bit more information coming up on that. Next internal data structure is the string table. This again is a hash table. It's the same type of hash table that the system dictionary is. Its default size is also 1009. Intern strings are stored in the hash table. So if you are using more than 1009 intern strings, your performance is going to degrade. So why is that? So let's just take a look at what a hash table is here. All right, so the array on the left-hand side that's vertical to the screen is the size of the table. If you get beyond that size of that table, you start building bucket chains, and that's as we move to the right. The critical region for access is right there. Right? So if you're accessing just a single entry in the original array, your critical region is going to be very small. It's just a single access in that vertical array that you see there. If you go beyond that, you have to walk the buckets within the same critical region. So you can imagine, the longer the bigger that critical region is, the more time you're spending and the more of a bottleneck that is. So entries greater than n-1, your performance is going to degrade. So how do we know? How do we know the classes are loaded? How do we know how many classes are loaded? I mean, the rough estimate is to take a look at X verbose class and count the number of loaded classes. And that's a simple command line that allows you to do that, minus X verbose class, run your application, and then just count the classes. That give you a general idea of what you're loading. What that doesn't do is reloads and unloads. So that's the rough part of it. If you're unloading these classes, it's going to obviously you're going to reload them again when you need it, and that will show up in verbose class. How do you know how many intern strings that you have loaded? Well, that's actually much simpler. We have a flag for that. Print string table statistics, and that's new in update 4 as well. If you're running a large enterprise application, take a look at these two situations. It's worth it. I mean, we've seen, when we had an artificial environment that we were testing just to see what the performance impact would be. With 70,000 intern strings, we saw a 7 to 10% top line performance improvement just by setting that intern string table to the correct size. So that's just, if you're running into that problem, it's a quick fix. As time goes on, as time goes on in Java 8 and Java 9, because we have this flag, it's not a critical performance fix for us. But we would like it to be adaptive and something that you don't have to manipulate. Okay, code cache. I mentioned code cache. Default size is 64 and 96 with running tiered compilation. Okay, my internal net. How to check the code cache. Well, apparently I have a slide versioning issue. Thought I filled that out. All right, I didn't fill that information. So basically, what you're looking is for code cache, and I apologize I didn't have that in there, is you're looking about you want to know what is the capacity of how many classes or methods you've compiled. And the quickest thing is to look at print compilation and do a count. That will tell you an idea, give you a general idea. You want distinct classes that you're loading there. Distinct blocks that you're compiling, but that gives you a general idea. You can also take a look at using heap dumps. Take a look at the code cache itself and find out where you are. It's not necessarily a heap dump, but it does dump the code cache. If you do run out of the code cache, compilation does stop.
What do you mean stop? Is it throw an exception?
It says compilation failed in print compilation output, and it's not compiling anymore. That does not, so that's update 2 of 7. Before update 2 of 7, it would simply just stop. Now it starts kicking things out and makes it more difficult, frankly. So it's, I'd rather have it stop, but it's not, that's why tiered compilation is not on by default. Okay, permanent generation size. Okay, there are different 32-bit and 64-bit defaults. The 32-bit default is 8 megabytes. The 64-bit default is 32 bytes. That's the starting size. So how do you know if you're running out of perm space? The full GC events in print GC details, if you use the print GC detail flag, and if you take a look at at a full GC event, it shows you what the size of your perm gen is, because the perm gen was only collected at full GC. So that's where you're going to see the output. And you can set the initial perm gen size with perm size and the maximum with max perm size. Just a note, you've heard us talk about this in other talks. The permanent generation will be removed in JDK 8. It'll be moved into the heap. So this perm gen sizing is soon will be a thing of the past. Okay. We've talked about compressed oops a lot. So compressed oops is essentially using a 32-bit offset to reference it into a 64-bit heap. But there's actually several phases of compressed oops, so I want to give a little detail on what the differences are. Okay, if you're running less than a 4 gig heap with a 64-bit JVM, basically the heap is moved to the low virtual address space, which we can directly reference without encoding or decoding. So essentially, it is, we don't have to do a shift or anything along those lines. The fact that we're 8-byte aligned allows us to assume that we have a zero base for starting, and then it's just a direct offset. So if you're running less than 42, it is a direct offset. Essentially, it's a direct reference. If you're running less than 4 gigabytes, The performance of the 64-bit JVM is no different than 32-bit. It's clearly, it's the same. If your heap size is between 4 gig and 26 gig, that's where our full zero-based compressed dupes comes into play. And basically, we know all we have to do is a shift to decode the address. A shift is very fast on x86 and Spark. We see very little performance impact beyond 32-bit when you're up to 26 gigs. But there is a slight difference. It's not between 26 and 32 gigs is regular compressed dupe. So we don't have we can't assume that we have a zero base. So it's a bit more of a decoding operation. We have to do an add and then a shift essentially. Now, if you're running up to 64 gigs, it's the same as above, same as the 32 gig case, but you have to set this object alignment in bytes to 16. You can see the trick that we're doing, right? We're because we know we're 8-byte aligned, we're able to use that assumption to do a jump, to basically to do an offset into the heap to find the address. If we set it to be 16 bytes aligned, we can do the same thing up to 64 gigs. Fragmentation tends to be a bit of an issue. You have to be aware of that as you start to manipulate alignment. We have found that up to 64 gigs, the alignment impact, the fragmentation impact when setting it to 16 it's not dramatic. Now, if you wanted to say, hey, let's set it to 32 and go up to 128 gigs, yeah, it's problematic at that point. You'll find yourself rather fragmented. Okay, so I apologize. I have two sections where I'm mentoring large pages, and this section is a bit more detailed. So that's why I was a bit confused when I get to the last slide. Okay, so OS tuning. We'll get to that now. Large pages again. So you mentioned, is it only on Linux? No, large pages is actually fully supported on Linux, Windows, and Solaris. Linux and Windows, you need to do OS configuration tuning, and you need to specify the flag for the JVM. We don't do it automatically. So if you're running on Linux and Windows, the first thing you need to do is I have a blog that I wrote quite some time ago that tells you what you need to change on Windows and Linux. Linux has gone back and forth as far as what is required. So, the suggestions I have on this blog are pretty tried and true for hotspot. However, it is the old methodology. As far as the automatic coalescing of pages, it's a different term. I don't know the term, but essentially that's what they're doing in Linux. Let's just say it's not fully baked. So we just use it. This is the better way to use it on Linux. Solaris, it's been on default since Solaris 7, which is a long time ago. And what we do on Solaris is that we use the first specified large page size. When you're running x86, there is only one large page. With modern Intel systems, it's 2 megabytes. As far as the initial, let's say medium-sized page. So we always choose 2 megabytes on Intel. Now that you have the 1 gig page possibilities and so on, you can certainly specify that using large page size in bytes. But running on Solaris, we choose the 2 meg or the 4 meg or the 8 meg, depending on the platform that you're running on. And if you want to go higher, you can specify it. But in looking at performance deltas and differences between Linux, Windows, and Solaris, that's a good thing to note because we are trying to take advantage of the default the functional defaults on the operating system that we can. And large pages has been handled automatically on Solaris for quite some time. So that's why we've been doing this for quite some time. This is TLB pressure, and that's what you're alleviating by using large pages, is the hardware TLB pressure. It can have a significant impact on your performance. I saw a talk last night with folks from Salesforce, and they indeed saw significant benefit by using large pages. Okay, next for OS tuning is manipulating the scheduler. The Linux the completely shared fair scheduler, or I'm not forgetting actually what the acronym fully stands for, but once that came into Linux, that was actually made it a bit difficult for tuning. It tends to be a bit more client focused than task sharing and time sharing focused as on the server side. One of the things that you can manipulate are the scheduling policies and using groups with CFS. Groups with CFS is you can have a lot of success with that, so that's something that you can certainly look into. Next, as far as scheduler tuning is Solaris. The FX scheduling class is a scheduling class that tries to give equal time to all threads. And it is just equal time to all threads for the most part. It does manipulate the quantum as far as what you have, but each thread has the same time available on proc. And we have found that that is something that certainly is worth trying for enterprise type applications. Okay, memory allocators. I'm just mentioning Solaris here because we have a libumem that is worth trying. Libumem it shines greatly with highly parallel allocation. And you use the environment variables LD preload and LD preload 64, depending on the bitness of your application, to take advantage of that. Other deployment considerations is multiple JVMs. It's the classic, if a single JVM can't handle it, maybe more than one can. And the idea is that you're reducing the work of any single JVM. It is very successful at reducing overall maximum pause times, especially when you're using some of our parallel garbage collectors. The pause time that you incur with a garbage collection is directly related to the amount of live data that you have. So if you're able to distribute the live data across many JVMs, it's just simply going to be faster on those smaller JVMs. And that's the. See, I got the 5. So I made a mistake in this slide, actually. The default thread count is not 5/8, it's 5/16 now. Prior to 7 update 4, it was 5/8. So I'm skipping ahead, but another thing to consider with multiple JVMs, if you are indeed running multiple JVMs, is the parallel GC thread count. We have no awareness of other JVMs running on the system. So if every JVM is running 5/16 of the hardware threads, you end up having a boatload of threads running that you may not want to. So our general suggestion is that the total GC threads should be less than or equal to the number of hardware threads that you're running. And you have to specify that by hand using the parallel GC thread count. And there's the flag right there. Okay, now into GRE configuration. Just a couple tidbits as far as configuration is concerned. So updating the crypto provider on Solaris. Doing this will allow you to take advantage of some of the hardware crypto optimizations that we have with the later Spark and x86 CPUs that Solaris is supporting. So certainly, if you find crypto in your profile, then you might want to certainly consider this. And lastly, this is just another one: is if you're using temp. The default temp for Java is not typically the correct temp for your operating system, so setting it to the actual temp directory of your operating system might help performance if you're heavily using that. Applications that do dynamic compilation of bytecodes use temp quite a bit, so you want, our compilers use the temp space quite heavily, so that's where we found setting it to the operating system's temp directory is an advantage. Again, all of these advanced tuning parameters that I've went through are really, you're talking about the last 5% of performance for the most part. So of course, keep that in mind. Okay, that brings us to the GCTF section at this point. So I'm going to break over to and have Monica carry on and cover GC from here out. So here's Monica. Thank you.
So I'm going to talk about GC tuning, and I'm going to cover 3 GCs. Oh, lower, of course. Sorry. So I'm going to talk about GC tuning, and I'll try not to go fast, but there's a lot of matter that I'm going to cover, and so let's start. What's the number one goal for GC tuning? Try to collect as many short-lived objects in the young collection itself, right? And then there are others, and I'm going to talk about this more in detail later, but I'm just going to summarize it first right here. So you size your young generations to try to age the objects so that you can collect it in the young generation itself. Sorry. Then you size your old generation to try to fit your live data set. So what's your steady state live object size? Size your old generation to contain that. So our recommendation is that if you do have the heap, we would say anywhere from 1.5x to 4x, right? And you should be very careful about not spilling into swap space, because swapping will kill performance. What other things you can do? You can increase the survivor space so that, so yeah, you took care of your short-lived objects. What about your medium-lived objects? If you're promoting medium-lived objects into old generation prematurely, guess what? Now you need an old collection to take care of that, right? So try to size your survivors to age those medium-lived objects as well, so they collect them in the young generation itself, so you're not promoting them as much. But there's a word of caution when you're sizing the survivor spaces. Be careful that if it's too big a space, then some space can go unused. So if you have footprint issues, try to think about that in mind. So depending on your application goals and the type of collector that you select, heap sizes have a lot of impact on that. So when you have your goal, so what's your goal? Throughput, latency, footprint, right? So, and then you will select the collector accordingly. So keep selection of the collector, keep that goal in mind. And also remember the old generation collections are more expensive for some over the other. So choose your collector wisely. So talking about the latency and throughput trade-off, right? And think of a parallel collector as your throughput, and think of G1 as your latency, right? So what are the differences? Not incremental, more incremental. You know, what does that mean? It means that it collects the entire generation in one chunk, right? And that's non-incremental. More incremental, you'll have regionalized heap. So what's the benefit or downside, right? So you have long pauses when you're collecting the entire generation in one chunk. On the other side, you have more uniform pauses because you are collecting regionalized heaps, right? But then you have minimal overhead on the application thread. And what that means, that you're getting the best throughput pretty much, right? On the other hand, over here, you have more overhead on the application threads. So you get best latencies, throughput may suffer. So there's no one-size-fit-all GC. So let's kind of deep dive. So I'm tuning for throughput. So what is my suggestion, right? What will I do? I will let the ergonomic work for me. And that's my suggestion to you. Let the ergonomics work for you. And I'm talking about right now the parallel GC, which is the throughput GC in hotspot. So it's by design, it's supposed to have low GC overhead, right? So for example, the GC time ratio, which provides a throughput goal. So let's go back quickly. So what are the three goals? The goals are throughput, latency, low latency, minimum footprint, right? So for parallel GC, it's designed to have maximized throughput. So that's number one priority. And that's evident by the switch over here, which defaults to 99, which means that your throughput goal is 99, right? That means 99% of the application time and only 1 for GC. Also, the use adaptive size policy, which is enabled by default, it helps maintain the throughput goal by adaptively sizing your generations. There's something called a target survivor ratio, which defaults to 50, which means that only 50% of the survivor capacity will be collected at GC. And it also helps with having those spikes, object spikes, and the surviving object spikes, sorry. Again, how is it designed to have low overhead? You have something called a tenuring threshold, which helps age. I was talking about the aging of the objects. So with the help of this tenuring threshold, which is recalculated at every collection, it tries to maintain or reduce the copying cost and to reduce the overall cost of the GC. So, for example, if you're doing more work in the young generation, And then in the old generation, then guess what? The tenuring threshold is lowered to promote more objects into the old. So you're doing less work in the young, kind of. So it's designed to have low GC overhead. Now, what happens when the ergonomics don't work for you? So, well, we say tune by hand. So how do you do that? You maximize your heap space. Because if throughput is your goal, then you have to put footprint on the back seat, right? So you maximize your heap space. And we've seen, and I have done this myself too, and we've seen that. People do keep their initial heap and their maximum heap to the same value. How does that help? Well, whenever you need to grow your heap, or even shrink it for that matter, you will be doing a full collection. So to avoid the full collection, guess what? People do that. But then I've also, so my suggestion is this. If you are throughput minded, so and footprint is not the issue, allow that little, in just in case situations, keep your maximum heap at that. And whatever heap you think that your application needs, set your initial heap to that. So guess what? So you're doing good, but then you won't be having an out-of-memory exception, right? Yeah, you will get a full GC, but at least you're not having that exception for this just-in-case situations, which can happen. My second suggestion is to study your GC logs. That's what I do, daily basis. I make sure the outputs have print GC details and print GC timestamps. And I size the generations by hand. If you do need the last 5% or 2% or whatever you need, I do that. So let's quickly look at the output here. We have, so I said the print GC timestamp, so that one shows right there, the timestamp. It shows the number of seconds since the launch of the process. So it helps you compare different logs. If you made some tuning changes, you can see, the timestamps right there. This area over there shows you the young generation information. So what's the occupancy before the GC occurred, occupancy after the GC, and the total size of the young generation. This one shows the Java heap before garbage collection, Java heap after, and the total size of Java heap. And then the time that it took for the GC to happen, right? Sorry, I'll just go back very quickly. There you go. Okay. So talking about sizing generations. So there's a switch called new ratio. It helps you set the young to old generation ratio. And smaller value indicates that you need more space for the young generation. So for example, right here, if you have a new ratio of 2, that means you want 2/3 of the total heap for your old generation and 1/3 for the young. If it's 3, it's 3/4, 1/4. Something to keep in mind. So I've also seen, and I've done this myself too, keeping a fixed value of nursery and higher fixed value of nursery, and then letting it grow from from the minimum nursery to a maximum nursery. And why do people do that? It's because in most cases, young generation has the most effect on your throughput. But when you're being too aggressive, with generation expansions, you gotta be careful. Try to maintain, again, GC overhead directly relates to throughput. So try to maintain your GC overhead lower than 5%. In fact, later on, I have an example in the low latency case that the overhead is also important for latency, and people, it takes time to connect those two together, but it is true. So how do you fine-tune the young generation yourself? Disable use adaptive size policy and tune by hand. So usually applications with steady behavior usually don't need it anyway. And one word of caution, heap will not grow from its initial size. So if you set the heap at initial size and you disable use adaptive size policy, your heap will not grow. So now you disabled your adaptive size policy. What do you do next? Look at the output of adaptive size policy to study the behavior, and then you fine-tune it by yourself, right? So what does it show? This is an output of adaptive size policy right here with parallel GC. And what does it show? It shows you the survived, how many bytes survived, how many bytes got promoted, and the overflow. Did anything overflow That means it overflowed the survivors and had to be promoted now because your survivor spaces were not sized properly. So in this case, it's false, which means nothing overflowed. But then if the switch is true, that means you have a problem. Or, you need to tune it, basically. You probably don't have a problem yet, but you need to tune it. Second, another suggestion is to look at your print engineering distribution to see how the JVM does its calculation of the ages, and then fine-tune it by yourself. So this is an example of print engineering distribution for parallel GC. It tells you the desired survivor size. It tells you the new threshold, which is the age threshold, and what's the maximum threshold. So, and of course, the same print young GC outputs that we've seen before. Okay. So when you look at the output of print engineering distribution, what can you do? You can initialize your initial engineering threshold, or your max tenure. You can change the value of your max engineering threshold. You can lower or increase it based on the application's distribution. Now you know that in steady state, my aging is X, and then I can adjust these two so that I don't start at a low initial value, or I don't need to go up to the maximum. So you can tune that yourself. And you can also tune, based on the last two flags that I mentioned, you can also tune survivor ratio as such. So what is survivor ratio? Survivor ratio determines the size of survivor spaces. And how is that calculated? The survivor size is equal to your nursery divided by the survivor ratio plus 2. Why 2? Because you have two survivor spaces, the from and the to. And why would you use this? So remember, any overflow, it gets promoted to the old generation, which can overload the old generation, right? And large survivor spaces are needed for transient data. So it's not your live data set that's going to remain with you. It's just transient. It's medium-lived objects. So you want to just age them there. You should age them in the survivors, filter them out, don't promote them, right? That's the goal. So I'm going to talk about G1GC as a throughput collector, yes. So I know G1GC is known to many as a low latency collector, but yeah. So let's see how we do that. My first, and I'm going to repeat this again, most important thing, understand the defaults. G1 does have these defaults, and they're there for a purpose. Try to understand them. So there's the maximum and minimum nursery default, which is 20% and 80%. So your basically nursery will go from 20% of your heap to 80% of your heap. And there's a maximum pause time target, which defaults to 200 milliseconds. So note, when you're doing this tuning and you're setting an XMN, I know we did this for throughput just about 2 slides ago, right? But doing that for XMN, for G1, has implications. First of all, everybody should know that when the Java heap expands, you have just fixed your nursery on the command line. So your nursery is not expanding. Your heap is expanding, and nursery still. So like I said, most of the applications, your nursery plays an important role for throughput, right? Another thing is we're talking about defaults. G1 is new to the throughput game. We all know it. So for example, right here, the GC time ratio that I was talking about earlier, which was 99% of application time for parallel GC, guess what it is here? It's 90%. So yeah, we don't care about it. We don't care for that 9%, right? It's funny, but it's true. That's what the default is. So what do you do after you understand the defaults? You try to manage the GC overhead. How do you manage the GC overhead? By expanding the heap. But again, too aggressive an expansion will hurt throughput. So be careful about that. Another thing with G1 is that, so again, remember those priorities again. G1 is designed with low latency in mind. So low latency comes first, throughput, footprint, right? So don't set really aggressive pause time targets. If you have throughput in mind, then let your pause time relax a bit. Why is that? Because when you set an aggressive pause time target, it indicates that you're willing to have more GC overhead. More GC overhead means that you're okay with lower throughput. Okay, managing the GC overhead again, try to tame your mixed GCs. I have some examples in the low latency section about this. So these are the flags that I use. There's more, but these three are really, really important for everybody to know. The first one is initiating heap occupancy percent. What does that do? It starts a marking cycle when the heap, the total heap, not just the old generation, the total heap reaches that threshold, which the default is 45%. The second one, G1 mixed GC count target. What is that? It's the maximum number of mixed GCs that will be performed after a marking cycle. The default here is 4. And what's the third flag? The G1 old CSET region live threshold percent. It's a mouthful. So what does that do? So live threshold percent. So there's a live threshold percent of, I think, default of 90. So that many regions which have 90% of live data will be considered in a collection, in a mixed GC collection. So guess what? You can reduce it. If you think those are getting very expensive, mixed GC counts, mixed GC times are getting more expensive, so reduce that. Drop that to lower, 65. Experiment with it. We're going to move now to tuning for low latency, and I'm going to talk about CMS tuning, because that's the low latency collector right now that people are using for hotspots low latency collector. So first thing you need to know about tuning for low latency is know your pauses. You should know your average pause, your maximum pause time, and the frequency of pauses. So, and monitor your GC time. You know what the young collector is for CMS? It's parallel new collector. Par new collector. So you're having stop the world pauses. So monitor your GC times. Maybe that is the problem, right? Resize your young generation. It's basically similar, par new is similar to parallel throughput collector, right? So resize your young generations based on the pauses that you see. Young generation too long, decrease your young generation. It may not work for all cases. Young generation too frequent, increase your young generation. With CMS, you have to be really careful about premature promotions because promotions in CMS are very expensive because we have free lists as compared to TLabs. And the more often we promote and then reclaim, guess what? We're setting ourselves up for fragmentation. So it will creep in. So I've seen applications, and in fact, on Sunday we were talking to somebody, and he said that they do that too. They use CMS as a safety net. So they're doing mostly young collections, and for this, just in case, guess what should I do? Oh, well, we'll just use CMS as a safety net. And some people also schedule full GCs at non-critical times. CMS, the important issue, decrease the likelihood of fragmentation. Sadly, you can never eliminate fragmentation, but you can decrease. How do you do that? You can decrease promotions into the old generation. Usually large objects of various sizes are the main cause of it, so be warned. You can reduce the CMS cycle duration by tuning parallel CMS threads, but you will see more concurrent overhead. But again, I guess you had low latency as your number one pastime goal anyway. So CMS will automatically try to find its best initiating occupancy. What does that mean? That it first tries to do a CMS cycle early enough to collect the stats. Then it tries to start the cycles as late as possible, but early enough not to run out of heap before the cycle completes. It keeps collecting stats and adjusting when to start the stats. Sometimes it can start too late, unfortunately. These are the flags that you need to know. The first one is initiating occupancy fraction, which is the size of the occupancy of the old generation, not the full heap, the old generation that triggers the CMS cycle. The second one is telling CMS not to use as ergo, which I just mentioned a slide earlier, not to use that and use what you just said on the command line up, the first one. Excuse me. And then the CMS initiating perm occupancy fraction, which is the occupancy of the perm gen that triggers the CMS cycle. And class end loading has to be enabled for this. Now talking about G1 as G1 tuning for low latency. Again, understand your G1 defaults. Use them to your advantage and use that to minimize the command line options. Remember that XMN I was talking about earlier? Just by setting XMN, guess what you did? You are no longer caring for pause time target. You're telling that this is my XMN and my pause time target is out the door, right? So be careful about that. If the defaults don't work for you, then you set your pause time targets yourself. You can also set your pause frequencies and look at the GC logs and see if you're getting the most of your pause time goals. I have some examples next. So in this particular example, the heap restrictions, so basically they were footprint, trying to contain their footprint. It was stretching the pause time goal. So we're working with heap space of 2.5 gigs, and G1 was not able to accommodate the live data set. So guess what we were having? We were having promotion failures and evacuation failures, and we were having full GCs as a result. And that's how it looked on the left-hand side. So what we did first is calculate the live data set, and we made sure that the old gen can accommodate that, and that's how it looked afterwards. Now, same example, after we tuned it, guess what? It's still not meeting its pause time target, which was the default of 200 milliseconds. You see, the young generation, so I'll take a step back. The red is young generation collections, and the greenish blue are mixed GCs. So mixed GCs were blowing the pause time target, and the young generations were all nice and good, right? So then what we do, we tame the mixed GCs, as I mentioned a couple of slides earlier. And this is the slide that I was talking about the overhead. So GC overhead is above 5%. And guess what it was doing? It was affecting, of course, it's affecting your throughput, right? We know there's a direct relationship. It was also affecting the average response time and the 90th percentile response time. So we worked with taming the mixed GCs, as I mentioned earlier, and we brought it down. So, and it kind of helped them a lot, actually, but just bringing it down below 5%. Getting the most of your pause time goals. This is the switch that you use to set your pause time goal if you don't want the 200 milliseconds default. It provides a hint that pause time goals of n milliseconds are or less are desired. G1 will do its best to meet the pause time goal. How does it do that? It adjusts its young generation. Remember the 20% and the 80% default for the young generation? It'll try to adjust that. It'll try to size your heap. So if it's increasing the heap or whatever, it's taking care of the young generation. The young generation, 20% to 80%, is going to move with the size of the heap. And there are other related parameters to try to stay within the goal. Don't let mixed GCs stretch your goals. Lot of old regions can make mixed GC pauses longer. You should understand what triggers a marking cycle. If the defaults don't work for you, you should modify them. I have about 8 minutes. So this is how you select the start of a marking cycle. Remember the initiating heap occupancy percent, which defaults to 45. So you can manipulate that right here with that command line option. If you start your marking cycle too early, you'll have high concurrent overhead and frequent mixed GCs will incur. If it's too late, guess what? You're dooming yourself for an evacuation failure and a full GC down the line. And set it to a higher value so that you can hold your steady state life size in the old generation. We'll talk about tuning for footprint. These advices are applicable to all GCs. A, know your live data set. We spoke about that briefly. Know your promotion rate and know your allocation rate, right? So live data set, it should fit comfortably in your old generation. If not, guess what? You're going to have expensive full GCs down the line. Promotion rate, why do you need to know that? So you can age, if you know that it's just, you're promoting more, you're promoting medium-lived objects as well. So you can size your survivors accordingly. allocation rate. You need to know, is it just steady, or we have allocation bursts or something like that, and then adjust your heap sizes accordingly. How to calculate allocation rate? So so you have to do this for the log. Once you know your steady state window, I'm just showing 2. So what you do is you look at your current allocation, basically whatever objects were before the GC in the young generation, and the previous GC post objects. You subtract that and you divide that by the time difference, and that's the allocation rate right here. Promotion rate right here. So what is promotion rate? Whatever is getting promoted to the old gen. So basically you're subtracting the old gen occupancy now to the old gen occupancy before. And since the print GC details output only gives information about young generation and the total heap, so basically so total heap is equal to young generation and old generation, and that's what we're trying to do. We're trying to subtract that values just so that you know what got promoted into the old generation, and we use timestamps to get the frequency. So for this particular application, it's actually very good, right? We were doing 36667 megabytes allocation and 7.96 megabytes per second. We're promoting only that much. How do you know your live data size? Just look at the old gen occupancy after full GC. So you see after a full GC, the total heap and the old gen occupancy is the same value. It's 1.6 gigs right there because your young generation is 0. It gets collected fully. So there could be other contributors, right? GC is not always the issue, and we should be aware of that. Check the footprint of your entire process. Think of native libraries, thread stack, so many things, right? And then sometimes you may have to rework your application. You're working with footprint restrictions, but your object allocation and retention is not helping that cause. So you have to collect a heap profile and understand your allocation and retention, and then work on reducing them. Use more space-efficient data structures, check your input size. So I want it all, and I want throughput along with low latency, I want minimum footprint. Unfortunately, guess what? You have to sacrifice one in favor of the other two, unless, of course, you have limitless resources, which we all do. But the good news is not that I have seen this, that not 3 are always important. And you are the judge, and you know what's important for your application. So maybe this recap will help you choose. So remember, when you have larger heap, which is footprint, it means that you may experience fewer GCs, but based on your object liveness, it could take longer to collect. So you have pause time right there, you have the throughput consideration, and your heap, which is the footprint consideration. So we have about 3 minutes left, and we are the summary slide. Yay. All right, so we have a showdown today at 4:30. Dave will be there. We have a G1 GC performance tuning talk tomorrow at 8:30. I'll be there, and Charlie Hunt will be there. And then we have a talk on Wednesday at 10 a.m. Are your GC logs speaking to you? Kirk will be there. And these are the aliases. I want everybody to note these down. And if you have any questions, suggestions, please feel free to use, or just monitor them. You want to understand how to do it yourself. There are people using these aliases. There are people replying. I reply. Many of my colleagues reply. Developers reply on these. So you understand the process. So monitor them at least. Well, that's all I have to say.
I think we got time for, thank you.